Hi, today I'll present our work on unsupervised learning of compositional energy concepts. The world around us consists of many different types of factors and variation. On one hand, we have a set of objects in the world, such as rulers, lamps, or gloves, which can occur in many different instances. For example, my table may contain several different instances of a ruler. On the other hand, a room also contains different global factors of variation. For example, the underlying lighting, reflectance, or material of the overall room. In this paper, we are interested in discovering in an unsupervised manner both the underlying objects in the room as well as the underlying global factors of variation. Prior work has explored this, but is concept specific. In particular, one class of work, such as Monet or slot attention or others, focuses on representing each object as a different slot, which is inferred from the input image. In contrast, to discover the underlying global factors in an image, approaches such as the beta VAE and related approaches embed input images into an underlying latent space, where the underlying latent space captures each of the inherent global factors of variation. In this paper, we are interested in discovering in an unsupervised manner these concepts in a unified way, such that on one hand we can discover these objects, but also on the other hand we can discover global factors of variation. In this talk, I'll first describe representing concepts as energy functions, then our underlying approach for discovering these energy functions unsupervised, and end with a set of results showing the applicability of our approach. First, let's consider how we may represent a concept as an energy function. We define an energy function as a function that takes as input an input image and assigns the energy to it. For example, let's consider a supervised energy function, a smiling energy function. This energy function will take in a frowning face and assign high energy to it. In contrast, it will take in a smiling face and assign low energy to it. We may generate from an energy function representing a concept by minimizing the energy of an input image with respect to the output energy. This minimization process allows us to find an image that the underlying energy function assigns low energy to. For example, consider an image that starts as noise on the left. After optimization, we'll gradually refine to a face of a person that is smiling. By defining energy concepts as energy functions, this gives us a natural way to compose several energy concepts together. In particular, now consider a set of different energy functions, maybe one for smiling and another one for a female. If we add up the energy functions for each of these to get a joint energy function, E of x, minimizing this function, E of x, then generates a sample that satisfies each of the constraints specified by the different energy functions, enabling us to generate a face that is both smiling, female, and has any other concept we desire. Notice that these energy functions don't necessarily have to be global factors. We could have an energy function representing a single object or any other factor that we desire, either global or local. Next, we'll discuss how we can discover these energy functions in an unsupervised manner so that they may represent both, on one hand, objects, but on the other hand, also global factors of variation. First, let's consider again generation using a supervised energy function shown here. How can we learn this energy function in an unsupervised manner? One idea is to train these energy functions by autoencoding. In particular, we condition our energy function with respect to a latent extracted from an input image. We then train our energy function so that energy minimization on the input energy function reconstructs the conditioned image. In particular, we train on this reconstruction loss shown below, where we start with random noise and minimize the input image with respect to the underlying energy function for 10 or so steps, and then take the final output and encourage that to match the original conditioned image. Now, how can we learn to discover a set of compositional energy concepts which we can compose and recombine across different images as well as data sets? To do this, we use an analogous trick. We take an input image and encode it now as a set of different latents. We condition each of these separate latents on each of our individual energy functions to get a set of n separate energy functions. We add up these energy functions together to get an overall energy E of x. We then minimize the input image with respect to this energy function. And at the end, we train our energy network so that this optimization procedure reconstructs the original conditioned image. So we use reconstruction loss again to represent and learn these energy concepts. We notice that now we have extracted a set of n different energy functions, which we may recombine or recompose in any way we like. Now let's illustrate an example. Consider this input image right now. We first get an image for the red sphere, then the black cylinder, then the blue sphere, and then the black cube. Similarly, we can take an input image of a face, get a first energy function that focuses on the hair of the person, the second one focusing on the background, the third focusing on facial experience, and the fourth focusing on skin color. Again, these energy functions are learned in a completely unsupervised manner, and on the top discovers a set of local features describing the scene, and the bottom discovers a set of global factors that describe the underlying scene. Next, I'll present some results of our approach when applied to global factory discovery, again, completely unsupervised. Consider these three images. In what follows, we illustrate the gradient with respect to each of the inferred energy functions. The gradient with respect to the input image of an energy function corresponds to the factors that the energy function pays attention to. In particular, perturbing the input image by these specified values corresponds to the maximal change of the underlying energy function and corresponds to the things that the energy function pays attention to. So, to visualize what the first energy function pays attention to, we can see this in the gradient map here. Looking at the gradients, we see that this energy function pays strong attention to the underlying edges of the scene. For example, the edges of the sofa as well as the table. As a result, and through additional recomposing experiments, we posit that the first energy function corresponds to camera position. Next, we look at the gradients of the second energy function with respect to the inputs. This one we see exhibits stronger gradients to the underlying lighting of the scene. For example, in the bottom image, we see that the shadow has high gradient values. The third energy function exhibits high gradients with respect to the floor of the scene, corresponding perhaps to focusing more on the floor position. And finally, the fourth energy function exhibits stronger gradients with respect to the overall scene, suggesting that perhaps the fourth energy function focuses on a global factor that affects the entire scene, which we posit to be lighting intensity. If we optimize with respect to all four of our inferred energy functions, we find that we are able to recapture the original image. Next, we do a similar illustration using faces. Taking the gradient of the first inferred energy function, we find that gradient magnitudes are high for the underlying hair of the person, suggesting perhaps that the first energy function corresponds to hair. Similarly, when we take the gradients with respect to the second energy function, we find that the gradients are much higher for the background. The third one is higher for the underlying eyes and mouth, suggesting facial experience. And finally, the last one is stronger for the underlying skin, suggesting skin color. By optimizing with respect to all four energy functions, we are able to reconstruct the image. Finally, let's consider the inferred energy functions for the image on the left. If we just optimize and generate an image with respect to the first inferred energy function, we see that we get the black floor of the scene. If we optimize with respect to both the first and second inferred energy function, we find that our resultant image has both the lighting and the background. And finally, if we optimize all three of our inferred energy functions for the underlying image, we get both the floor, the lighting, and the underlying objects, suggesting that our set of inferred energy functions correspond to floor, lighting, and object. Given our global factors of variation, now let's see what happens when we recombine them. In this setting, we take a single image and infer each of our unsupervised energy functions. Now we take the energy function corresponding to camera position and vary it across different values, while fixing the remaining unsupervised discovered energy functions. We find that by varying this energy function, which we posit to be camera position, although it could be anything else, we find that we are able to successfully manipulate the scene and re-render it at different positions with similar lighting direction and intensity. We can do an analogous thing where we vary the energy function, which we posit to correspond to lighting direction, while fixing all other energy functions. By changing this energy function discovered in a completely unsupervised manner, we find that we are again able to consistently change the scene while keeping the camera position fixed and the lighting intensity. We can do a similar thing with the underlying lighting intensity. And here what we find is, again, the remaining factors remain constant while the lighting intensity is changed. Now let's try recombinating factors for faces. We can consider two images, one on the left and one on the right. By recombining the facial expression of image 2 with respect to image 1, we get an image where the image has all the other aspects of image 1 with the facial expression of image 2. We can do analogous thing with the background. Here we can take the first image and substitute the background of the second image with the remaining parts of the first image. Now let's explore our approach when applied to local factor discovery, that is, discovering the underlying objects of the scene. Consider these three images of Tetris blocks. We find that if we optimize an image with respect to only one particular energy function for each of the unsupervised discovered energy functions, each energy function exactly captures one Tetris block, either the green one, blue one, or purple one at the top. We can then permute these energy components across different images. And when we optimize this permutation of energy functions, we find that we are able to reconstruct the blocks at new positions, as shown on the right, showing that each individual energy function learns to capture a particular object. We can do a similar visualization with cubes from Clever. Here, consider these three images. If we visualize the gradient of the energy function with respect to each input image, we find that this energy function pays special attention to the underlying objects in the scene. Likewise, if we optimize an energy function to generate an image, we find that each separate energy function corresponds to an individual cube in the scene. Can we recombine these objects together across different images? Here, consider image 1, which consists of 4 different energy functions, and image 2, which consists of 4 other energy functions. We can add all 8 energy functions together and generate a scene with 8 separate objects. Analogously, take this image and this image, and again, we can combine all 8 energy functions together to generate a scene with 8 separate objects. Finally, let's consider recombining these energy functions across both global and local factors, as well as across different data sets. Consider a first data set consisting of a set of cubes and spheres. Now consider a second data set which has a bunch of trucks and pens. What we can do is we can take 2 energy functions learned on the first data set using one instance of COMET, and 2 other energy functions learned on a second data set with a different instance of COMET, and recombine them and get together. We find that we're able to generate a scene with both pens and cubes as well as trucks. Similarly, here we can do the same thing as well as this. We can also recombine both local and global factors. We can take these 2 images here, and by inferring both of them simultaneously, we can generate a scene with objects in one image and lighting of a second image, shown here, and here, and here. Please see our paper for additional details on how we can flexibly specify whether we generate either a local or global factor variation. In conclusion, we presented COMET, a flexible and general framework for discovering both global and local factors in a completely unsupervised manner that enables them to generalize well even across different data sets and different models of COMET. We believe future work could include further scaling these to higher resolution images. Thank you, and please check our website for additional results.